Hello! In this video, we are going to prove the following theorem. Let a be a negative real number. Then for all integers n, if n is even, then a to the power of n is greater than 0. And if n is odd, then a to the power of n is less than 0. Now let's first remind ourselves of some things before we get into proving this. First of all, we know for every real number a to the power of 1 is equal to a. For every real number a to the power of 2 is equal to a times a. And also, for every non-zero real number a times a is greater than 0. Or in other words, a to the power of 2 is greater than 0. Now, in proving this theorem, we are going to be using 3 preliminary results regarding integer exponents that we have proven. First, let a be a non-zero real number. Then for all integers n, a to the power of n is a non-zero real number. So this is telling us if we take a non-zero real number and raise it to the power of any integer, the result will be a non-zero real number. Second, let a be a non-zero real number. Then for all integers m and n, a to the power of m times a to the power of n is equal to a to the power of m plus n. Finally, let a be a non-zero real number. Then for all integers m and n, a to the power of m to the power of n is equal to a to the power of m times n. Okay, so now let's get into proving this theorem. To start off the proof, let's give ourselves an arbitrary integer n. From here, we are going to prove if n is even, then a to the power of n is greater than 0, and if n is odd, then a to the power of n is less than 0. Let's start by proving the first one. To prove the first one, we will suppose n is even. Well then, n is equal to 2k for some integer k. Now since a is a non-zero real number, we know that a to the power of k is a non-zero real number. So if we take a to the power of k raised to the power of 2, that will be a positive real number. But notice, a to the power of n is a to the power of 2k, and we know we can re-express the 2 times k as k times 2. So now we're in a position to apply our third result. This is the same thing as a to the power of k to the power of 2, which we know is greater than 0. So we see that a to the power of n is greater than 0. So we have shown if n is even, then a to the power of n is greater than 0. So that proves number 1. Now let's prove number 2. As for number 2, we will first suppose n is odd. Well then, n is equal to 2k plus 1 for some integer k. Now, just like we did in the first case, since a is a non-zero real number, we know that a to the power of k is a non-zero real number. So we take a to the power of k, raise it to the power of 2, that will be a positive real number. But then, when we consider a to the power of n, well, that's just a to the power of 2k plus 1. By our second result, we could rewrite this as a to the power of 2k times a to the power of 1. We know a to the power of 1 is equal to a, but what is a to the power of 2k? We can do exactly what we did up here. We can re-express a to the power of 2k as a to the power of k to the power of 2. Just like that. Now, we know that a to the power of k to the power of 2 is a positive real number, while a is a negative real number. So when we multiply a positive real number times a negative real number, that will be a negative real number. So this shows a to the power of n is less than 0. That's it. We have shown if n is odd, then a to the power of n is less than 0. So that proves 2. And so this completes the proof. And so yeah, that's pretty much it for this video.